So we are going to learn about the formulas for these further aspects of equilibrium. Okay, for the first formula, okay, that I taught you, okay, was related to this Kw, okay, equals to concentration of H plus to the power of 2. Now, you need to know, okay, how do we get this? Yeah, because it's all originated from water. Okay, we know water is going to change into this. Okay, and I know if I want to represent this, okay, in form of Kc. Normally, we use in the past we use Kc. Okay, Kc equals to concentration of H plus times concentration of OH minus divided by concentration of water. Okay, but now, okay, you should know that the water, okay, is going to be the concentration is constant. So we are not going to include that in the expression. So it's going to be a special type of writing, which is going to be, we don't no longer use Kc. Okay, we actually use a special name Kw. Yeah, Kw is going to be concentration of H plus times concentration of OH minus. Okay, that is the reason why we have this. And okay, we know that this is going to be X, this is going to be X. Number of moles is going to be the same. So because of that, okay, we can just simplify this, okay, saying that this is also concentration of H plus. Okay, because I want to write this because I want to find out the pH, okay, especially the pH of water. Okay, to be specific over here, the pH of pure water. So in order to find the pH of pure water, you need to have the concentration of H plus. So I need to represent the OH minus in terms of H plus. So it is better to write down in this form. Okay, and this is how we get concentration of H plus to the power of 2 equals to Kw. So in this sense, okay, what is Kw? Kw is known as ionic product of water. And this ionic product of water is the same, okay, as Kc. They are not affected by other factors. They are only affected by temperature, okay, pressure, catalyst, concentration. They are not going to change the value of Kw. And this Kw, okay, they have found out the Kw for pure water at 298 Kelvin, they have found out is 1 times 10 negative 14. Okay, they have found out that. Okay, and okay, from this information, I can find out what is going to be the pH of pure water at 298. Okay, so this one, okay, you should know by now, okay, how to calculate pH. There is a formula, negative log concentration of H plus. Okay, some of you will be wondering why suddenly we use log. Okay, why log? Why negative log? This one, okay, maybe you have learned in maths, okay, but the reason why we introduce log, okay, log is 10 to the base of something. So whenever you replace the base, okay, you can actually find out, okay, you can get a good number. Okay, just take it, for example, I have the concentration of, let's say, HCl. Okay, concentration of HCl is going to be 0.001. Okay, this is going to be my concentration of HCl. And I know, okay, this is a very small number. Okay, and rather than just writing in terms of concentration 0.001, they have come up with a way to make the number to look more presentable, to make the number to look more nicer. Okay, what they have come up with is, okay, you take this value, concentration of HCl, okay, you put negative log, okay, negative log H plus, which is going to be 0.001. Okay, and what will we get? Negative log normally is log 10. Okay, so this is going to be 1 times 10 negative 3. Okay, if you're good in maths, you know, yeah, negative and negative is positive. Okay, so 10 to the power of 10. Okay, and then you have 3. So automatically this is going to become positive 3. Okay, so you see the number, this particular number is going to be represented by 3. This is fantastic. Okay, that is the reason why they include this negative log. Okay, because I want to change something, a smaller number, into a whole number. and you can plot the graph, okay, you can represent the data in a better way. That is the reason why they have included or why they have changed, okay, why there is a need to change them. Yeah, negative log. Okay, if you don't put negative, what will happen? Then you will have -3. We don't want that. Yeah, so it means you are changing it into a scale. Okay, like for example, all of us, okay, different people in this class, yeah, they will have different marks in exam. Maybe Kenneth have 60%, Erlin have 90%, so many marks. Okay, but if I can group them in an easy method, okay, saying that this one above 80 is A, then after that B, after that C, after that D. So I don't have a lot of marks. Okay, I can just represent them in a simple way to represent rather than writing like 93 point something something, 98 point something something. Yeah, I can represent in a more presentable way. Yeah, if you want to remember in that form, okay, please remember. Yeah, so the reason why we have to use pH, okay, because it's going to give you a different scale, okay, where you can represent the data in a better way. Yeah, how to use this, okay, pH negative log H plus, we can just straight away use, okay, in terms of water, pure water. Okay, we know that Kw is 1 times 10 negative 14. How do we know that? You no need to worry, it is given to you. Yeah, it's given to you. So you just need to apply and learn how to use only. So if you have this concentration H plus, you go and find out the concentration of H plus is what? Okay, square root. Okay, if you square root, you will get 1 times 10 negative 7. Okay, so this is the concentration of H plus. So now, if I'm looking for pH of pure water, and this pure water is going to be at 298, I can find out, okay, by just using the formula pH equals to negative log concentration H plus. And this is going to give me negative log 1 times 10 negative 7. You can use calculator, or here directly you can see the pH is 7. Okay, this is how we can prove, okay, the pH of pure water is 7. Okay, so we just have to find out the H plus. Okay, so we have to find the H plus. And do remember, these two formulas are very important. Okay, this is more universal because you need to know how to calculate the pH. But this Kw, okay, we are going to use it for finding the pH for both, okay, for both acid and base. And we are going to talk about strong acid and strong base. Okay, what is strong acid and strong base? Let's say, for example, HCl. They give you H plus and Cl minus. So if you have 0.01 mole per dm cube, yeah, you can find out. Very simple, 0.01, 1 mole to 1 mole. Okay, I know the concentration of H plus. Just apply. Okay, just apply directly. pH equals to negative log concentration of H plus. Straight away you apply. And then if you have NaOH, I hope you remember this. Okay, if you have NaOH, I know NaOH is Na plus and OH minus. Okay, I don't have H plus. So how do I get? Let's say the concentration is 0.01. Okay, I know this is 0.01, 0.01. Okay, whenever you have sodium hydroxide, whenever you have potassium hydroxide, okay, you can use two methods. Okay, two methods. One is going to be the method of using Kw. Okay, why? Okay, we are going to, in general, we have water. Okay, the Kw don't change, okay, unless you change the temperature. So now this is pure water. In pure water, I'm going to add sodium hydroxide. Sodium hydroxide has OH minus. So I am including OH minus into water. Okay, so this water, okay, earlier, okay, I know the Kw, okay, Kw is going to be concentration of H plus and OH minus. Previously, in pure water, I assume that this is the same, but now no more. It's not going to be the same anymore. Okay, why? Because I'm adding the OH inside. Okay, I'm going to add the OH, but do remember the good thing is the Kw don't change. Okay, the Kw remains the same. So the Kw is still going to be for water, 10 to the power of negative 14. H plus is the one that I am going to look for to calculate the pH. OH minus is no longer going to be the same as H plus. Okay, what will happen? Okay, because you have the water, okay, they give you this, okay, they give you this. And there is going to be additional OH that is on top of this water. There is going to be additional OH that is coming from the NaOH. And there is an assumption over here. Okay, what is the assumption? Okay, we are going to ignore, okay, the OH from water. We are just going to just take it. There, all the OH, okay, is going to come from the NaOH. Okay, so here, okay, I'm not going to worry about the OH minus from water. It's too little, okay, too little. So they just use this 0.01. Okay, why they use that? Okay, because generally when you have this water, when OH minus is increased, why? Because I'm adding NaOH. And when that is increased, the position of the equilibrium will be shifted to the left. Okay, and this will actually re-establish a new equilibrium. Okay, and the Kw, okay, because the concentration changes, Kw remains the same. So basically, they will readjust the system so that you are going to have a different value of H plus. So we can calculate that H plus. You can calculate directly. Okay, concentration of H plus equals to 1 times 10 negative 14 divided by 1 times 10 negative 2. This one I change it a bit. Okay, so it's 1 times 10 to the power of negative 12. And I can straight away, okay, calculate the pH. pH is going to be negative log H plus. And that is going to give me negative log 1 times 10 negative 12. That's going to give me 12. So this is how you use, okay, the method, okay, the Kw method, okay, to calculate. And there is another method which I taught you. Okay, in order to do this, if there is no H plus, what you do, you just change the pH formula into POH. POH negative log concentration of OH minus. And OH minus, you know, okay, 0.01. So you just need to put negative log, okay, 1 times 10 negative 2. Okay, you change it. Okay, and then you will get the POH is going to be 2. Okay, once you get that, okay, very important, if you want to use this method, you should know the relationship between pH and POH. pH plus POH is always 14. And you can calculate the pH because that is what we want to do now. Yeah, so 14, POH is 2, so you just calculate, you get 12. 12, 12. Okay, there are two methods to find out. Yeah, so this one I went through already with you. Okay, the next thing, okay, that I want to teach you, yeah, we have learned about these two formulas, and do remember all these are going to be related to strong acid and strong base. How when we deal with weak acid and weak base, okay, in your syllabus, you do not need to worry about weak base. Okay, weak base, no need to worry. You just need to focus on weak acid. And this weak acid, similar, yeah, like for example, how the formula that we need to know is going to be this formula. And I'm going to show you how we can come up with this formula. How did we come up with this formula? Okay, so basically, if you have a weak acid, okay, we write it as HA. And then they are going to have a reversible reaction to give you H plus and A minus, partially dissociated. Okay, partially dissociated. And when I write down in the past, what we do is just write Kc equals to concentration of H plus times concentration of A minus divided by concentration of HA. I am not going to eliminate HA. Okay, why? Because this is not constant. This is aqueous. Like just now Kw, I eliminated water. Okay, because why? Water is constant. Okay, this is aqueous. Okay, you do not eliminate, you just keep it as it is. This is the actual formula, but everyone should know also, okay, if this is 1 mole, okay, don't go and write down this as 1 mole and 1 mole. This is not going to happen. Why? Because it's partially dissociated. Okay, partially dissociated, it means it's similar with the method ICE, okay, initial change and equilibrium. Okay, whatever it is, okay, whatever it is, it's going to be less than 1. So I'm going to remove this maybe, okay, if this one is 0.01. Okay, because it's 1 mole of H plus and 1 mole of A minus, the concentration of this A minus is also going to be the same. This one you need to know. Okay, it's going to be the same. Because of that, okay, because we want to find out the pH, we don't want to actually include this A minus, okay, because I can just simplify this saying that concentration of A minus is the same as the concentration of H plus. I can change this formula into concentration of H plus times concentration of H plus because it's same. Yeah, it's going to be the same. Divide by HA. So you have that formula which is going to be concentration of H plus to the power of 2 divided by concentration of HA. Okay, but okay, when we reach into this conclusion, this formula, okay, there is going to be assumption. Okay, but before that, Kc, this one we don't refer it as Kc anymore because it's a weak acid. It will show us how much H plus is dissociated into the solution. So we say Ka. It's a special, like something like Kw. What is Ka? Ka is known as acid dissociation constant. Okay, so this is going to tell us, okay, it's a constant. Okay, so it means at certain temperature, the Ka is going to be always be the same. Okay, but do remember Ka something similar with Kw and Kc. They are not affected by other factors, but they will only change when temperature is changing. Yeah, so this is going to be acid dissociation constant, but there is going to be assumption for this formula. Very, very important. What is going to be assumption? The assumption is, again, similar like water earlier. Okay, you have water, pure water, and then I am going to add acid. Acid will be only valid, it's going to behave as an acid when you have water. Okay, so it means I'm adding acid into water. Okay, it means, okay, if you have HA, they give you H plus and OH minus. We know that water also will give you H plus and OH minus. But okay, in this formula, we only take the H plus from where? We only take the H plus from here. Okay, so what we did over here, we ignore this H plus. That is going to be the first assumption. Okay, we ignored that H plus. That is first assumption. Second assumption is, okay, we know that HA, okay, like just now I told you 0.01, 0.01, this one is from 1. So if you use the ICE method, okay, initially this is 1, this is 0, this is 0. So this is the change 0.01, change is 0.01. The change over here must be minus 0.01. Okay, so 1 minus 0.01, you will get 0.99. Okay, and here you will get 0.01, 0.01. Okay, what we supposed to do when we replace in the formula? Yeah, we are using this one. Okay, and we are using this one. That's why it's to the power of 2, right? Okay, but okay, when we use the HA, we do not use 0.99. Okay, we don't use that. What did we use? We will use 1. Okay, then this is going to be another assumption. The assumption is the dissociation, okay, of this is going to be too small. Okay, the dissociation is too small. We are going to ignore, okay, that there is no dissociation at all. Okay, it means instead of using 0.99, the assumption is we take the initial concentration of the acid, initial concentration of HA. So that is going to be another assumption. Okay, so I hope you can understand this part, the assumption, yeah? Okay, my internet connection. My yeah, my internet always like to give me problem whenever I'm doing something important. Okay, hold on, yeah. Let me share the screen again. So here, okay, our assumption is, okay, we are going to use, okay, if I summarize this, what are our assumptions? the assumption is number one, okay, I am going to ignore, okay, the H plus, okay, that is from water. Okay, that is going to be my first assumption. Okay, my second assumption is, okay, I am going to say that the dissociation, okay, the dissociation of that weak acid is too small. Okay, too small. So I am going to assume that the weak acid did not dissociate at all. And practically, you know, it's not true. Yeah, it is dissociating. So I'm going to actually say it's too small. So therefore, okay, we take the initial concentration. So it means we assume that there is no dissociation, okay, which doesn't make sense. Okay, but it's too small. Yeah. So initial concentration of the acid. Okay, this is going to be very, very important when we use this. Okay, we always use this whenever we are dealing with weak acid. The moment we deal with weak acid, automatically this formula is supposed to come in. Okay, so why this formula is supposed to be automatically coming in? Because Ka is only valid for weak acid. You don't have Ka, okay, for hydrochloric acid. Okay, you won't have that situation. Okay, you won't have Ka, okay, when we are dealing with H2SO4. Okay, you don't have. Okay, because Ka is what we call as acid dissociation constant. It's a measure on how much, okay, the acid is dissociating. Okay, you do not need to measure how much the acid is being dissociating when you are dealing with HCl. Why? Because HCl is going to be completely dissociated. So you do not need to actually measure that dissociation. Okay, so this Ka is only valid for weak acid. Okay, weak acid. And I told you, how about weak base? Okay, you do not need to learn in your syllabus. Okay, it is not going to be in syllabus. But if weak acid, if we use Ka, yeah, then weak base we supposed to use Kb. It's the same formula only. Yeah, but they will not ask you. Yeah, you do not need to know about it. Okay, and if you look at it, yeah, I can summarize. Okay, I mentioned about the weak acid over here. And then the last one is, okay, the pKa equals to negative log Ka. It's similar to your pH formula. Okay, pH formula is pH equals to negative log H plus. So why we suddenly need to change this? Yeah, just to make it as a cool number, something that presentable. Yeah, if you have 0.00, yeah, if I can get a whole number and it's nice to be presentable, yeah, they want it like that. And the function is going to be similar to your pH. If your Ka, okay, if your acid dissociation constant is more, okay, what does it mean? It means that my H plus and my H plus and my A minus is more. It means if I represent it over here, this is more. Okay, if you have the Ka to be more. Okay, so what does it mean? It means it can dissociate more. Okay, it means that my weak acid is a better acid. What do I mean by better acid? The weak acid can dissociate to give you more H plus. Okay, that is the meaning. So if your Ka is more, okay, I can just simplify and saying that this is a better weak acid. So I can simplify. This is a better weak acid. Yeah, but I can also represent the Ka in terms of pKa. Okay, if I have pH, okay, pH 1 and then pH 5, I can tell that pH 1 acid is going to be a stronger acid. Why I say it's a stronger acid? Because the concentration of H plus is more. That's why it will give you pH 1. So now, if I have pKa equals to 1 and pKa equals to 5, what I can deduce from here? I can say that this is smaller and that therefore, okay, the Ka is bigger. Something like H plus just now. Okay, so if the Ka is more, it means that they are going to be a better weak acid. So in summary, what I can say? Okay, I can say if you have more Ka, it means it's a better weak acid. They will dissociate more. Okay, and this is also valid if you have pKa value that is going to be smaller. The smaller pKa value, similar like pH, the smaller pKa value, better is the weak acid. Why? They will dissociate more. Okay, so you just need to refer or memorize this. Yeah, so it's going to be either bigger Ka or smaller pKa. Okay, both of them means the same thing. Okay, means the same thing. It's like if you represent, if you compare with acid, if it is more H plus, okay, so it's a better acid. Okay, they have more H plus, concentration of H plus. So it means because of that, the pH, okay, the pH is lower. So lower the pH is better acid. Yeah, but this one I'm using Ka and pKa because it must be for weak acid. Yeah, Josh.
For this one, we're saying it's a weak acid because it forms an equilibrium mixture between the H plus ions and like the non-dissociated one, right?
Yeah.
So if we said it was a strong acid, we'd be wrong. So we say
definitely wrong. Yeah, because that's why when we start this chapter, right, we have a strong acid, strong base, weak acid, weak base. So if you refer it as a strong acid means completely dissociated. So this is all these acid that has Ka, they do not get completely dissociated. So it's definitely wrong to say strong acid. Okay, but you can say let's say compared to A and B, B is a stronger acid than this. It's still fine. Okay, if you compare. Okay, but both of them, okay, must be weak acid. Okay, because the moment you use Ka, it is weak acid. Okay, so that is something that you need to know. And another thing, some students have problem because they don't know which formula to use. Okay, to calculate the pH. You need to identify the moment you see a particular acid, you should know that this is going to be weak acid. So in order to do that, yeah, you need to try read, you need to practice. Okay, what are the weak acid that we know? All carboxylic acids are weak acid. Okay, what else? Your H2CO3 is a weak acid. Okay, stronger acid HNO3, H2SO4, HCl, all these are stronger acid. Okay, so you need to find out. Okay, you need to identify first whether they are going to be weak acid before using the formula. And each different weak acid will have their own Ka. Okay, they will have their own Ka, and normally they will be provided to you, or you need to calculate them using the information that is given to you. Yeah, this is what I have discussed with you yesterday. Yeah, so now, okay, I am going to go forward, okay, to